Is string theory the key to unlocking the universe? In the quest for a unified theory that can explain all fundamental forces and particles in the universe, string theory has emerged as a leading contender. It proposes that the basic building blocks of the universe are not point-like particles, but rather tiny, vibrating strings existing in multiple dimensions beyond the familiar three of space and one of time. We will explore the foundations, promises, and criticisms of string theory, assessing its potential as the ultimate theory of everything. While string theory elegantly unites general relativity and quantum mechanics, its lack of experimental verification and the vast landscape of possible solutions present significant challenges. Recent advances in holography, cosmology, and the Swampland program suggest a dynamic and evolving field. Ultimately, we argue that while string theory offers compelling mathematical frameworks and deep insights, its status as the definitive key to unlocking the universe remains an open and critical question. What is the universe made of? This profound question has driven centuries of scientific inquiry. Classical mechanics, quantum field theory, and general relativity have each provided insights into different scales of physical reality. However, a complete and consistent unification of these frameworks remains elusive. At the heart of this challenge lies the incompatibility between general relativity, which governs the large-scale structure of the universe, and quantum mechanics, which rules the subatomic realm. String theory has emerged as a bold and ambitious attempt to reconcile these foundational pillars of modern physics. At its core, string theory replaces point-like particles with one-dimensional strings whose vibrational modes correspond to different particles. The theory naturally incorporates gravity, suggests the existence of extraspatial dimensions, and aspires to be the long-sought theory of everything. But is string theory truly the key to unlocking the universe's deepest secrets? Despite its mathematical elegance and conceptual appeal, string theory has been criticized for its lack of experimental validation and its seemingly infinite number of possible solutions. In this video, we examine the scientific foundation, strengths, and challenges of string theory in order to assess whether it can fulfill its promise as the ultimate explanatory framework for the cosmos. String theory originated in the late 1960s as a theoretical framework to describe the strong nuclear force. Early versions of the theory, particularly bosonic string theory, failed to account for key aspects such as fermions and required 26 spacetime dimensions, making them unsuitable as complete models of nature. However, the development of superstring theory in the 1980s, which incorporates supersymmetry, a symmetry relating bosons and fermions, revitalized interest by offering a more realistic foundation that requires only 10 spacetime dimensions and includes gravity as a natural consequence. By the mid-1990s, research in the field reached a turning point with the so-called second superstring revolution. This led to the unification of the 5 previously distinct versions of string theory into a broader theoretical framework known as M-theory, proposed by Edward Witten. M-theory suggests that strings are actually one-dimensional slices of two-dimensional membranes or branes existing in an 11-dimensional spacetime. In contrast to the standard model of particle physics, which treats fundamental entities as point-like particles, string theory posits that these entities are tiny vibrating strings. The different modes of vibration determine the properties of the particles, such as mass and charge, much like how different vibrations of a violin string produce different notes. For string theory to be mathematically consistent, it requires additional spatial dimensions beyond the familiar 3. In most models, the universe has 10 or 11 total dimensions, with the extra ones being compactified or curled up at scales too small to observe. These compactified dimensions are often modeled using complex geometric structures such as Calabi-Yau manifolds. Supersymmetry is a theoretical symmetry that relates bosons, force-carrying particles, and fermions, matter particles. Though not yet observed experimentally, supersymmetry plays a central role in string theory by canceling quantum anomalies and stabilizing calculations. If supersymmetric particles are discovered, for example at the LHC, it would lend significant support to the theory. String theory features various duality symmetries which demonstrate that seemingly different physical theories are actually equivalent under certain conditions. For example, T-duality shows that a small circular dimension is physically equivalent to a large one. S-duality relates weak and strong coupling regimes of different theories. These dualities suggest that all string theories are just different facets of a single underlying theory. Unlike quantum field theories of the standard model, string theory naturally includes a graviton, the hypothetical quantum of the gravitational field. This allows for a possible unification of quantum mechanics and general relativity, one of the main motivations for developing the theory in the first place. String theory is not merely an alternative to existing physical theories, it is a radically new framework that aspires to unify all known forces and particles under a single, consistent mathematical model. Its appeal to physicists arises from several compelling features that distinguish it from other approaches to fundamental physics. One of the most profound promises of string theory is its ability to unify all four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. In the Standard Model, gravity is treated separately via Einstein's general relativity, whereas the other three forces are described by quantum field theory. String theory offers a coherent framework in which gravity naturally emerges from the quantum behavior of strings, specifically from the massless spin-2 graviton. Additionally, different vibrational states of the fundamental strings give rise to all known particles, providing a potential explanation for the particle zoo of the Standard Model. In this way, string theory not only unifies the forces but also the matter content of the universe. String theory is admired for its mathematical beauty and internal consistency. Unlike many quantum field theories, string theory avoids certain infinities that typically plague quantum gravity calculations. Its framework forces a high degree of mathematical structure such as anomaly cancellation, supersymmetry, and conformal symmetry, which are essential for a consistent theory of quantum gravity. Furthermore, string theory has inspired major developments in pure mathematics, including advances in geometry, topology, and number theory. This deep interplay between mathematics and physics enhances its credibility as a fundamental theory. String theory provides powerful tools to explore black hole physics and may help resolve long-standing paradoxes. For instance, the information paradox, which arises from contradictions between quantum theory and the classical description of black holes, can potentially be addressed through the holographic principle and ADS-CFT correspondence. These ideas, rooted in string theory, propose that all information contained in a volume of space can be represented by data on its boundary, suggesting a radically different view of spacetime. String theory has also enabled the calculation of black hole entropy from first principles in certain cases, aligning with the Bekenstein-Hawking formula and lending credence to its quantum gravitational aspects. One of the most celebrated breakthroughs in modern theoretical physics is the ADS-CFT correspondence first proposed by Juan Maldacena in 1997. This duality relates a string theory defined in an anti-de Sitter space to a conformal field theory on its boundary. The implication is profound. A gravitational theory in a higher dimensional space can be equivalent to a quantum field theory without gravity in one fewer dimension. This correspondence has opened up new ways to study quantum gravity, strongly coupled quantum systems, and even aspects of condensed matter physics and quantum information theory, illustrating the far-reaching impact of string-theoretic ideas beyond high-energy physics. String theory has also provided tools to explore the early universe and cosmological inflation. Scenarios such as brane inflation, the string landscape, and string gas cosmology offer novel explanations for the origin and evolution of the cosmos. These models aim to address puzzles such as the initial singularity, the small value of the cosmological constant, and the structure of the multiverse. Despite its elegance and promise, string theory faces significant criticism, especially regarding its testability and empirical foundations. While string theory offers an elegant and ambitious framework, it has faced sustained criticism from both physicists and philosophers of science. These critiques center on its lack of experimental evidence, the vastness of its solution space, and questions about its scientific legitimacy. For all its theoretical appeal, string theory remains a highly speculative model whose status as a physical theory is actively debated. Perhaps the most significant critique of string theory is its absence of direct experimental confirmation. No unique, testable predictions have yet emerged that differentiate string theory from existing models. While the theory predicts phenomena such as supersymmetric particles and extra dimensions, no such signatures have been observed, despite extensive searches at high-energy particle colliders like the Large Hadron Collider, LHC. Moreover, string theory operates at the Planck scale, which is far beyond the reach of current experimental capabilities. This makes direct empirical testing effectively impossible with today's technology, raising questions about its status as a scientific theory in the Popperian sense. One of the most debated features of modern string theory is the string landscape. a vast set of possible solutions to the equations of string theory, estimated to number around 10, raised to the power of 500 distinct vacua. Each solution corresponds to a different way of compactifying the extra dimensions and leads to a different set of physical laws. This creates a significant problem. If the theory allows for virtually any conceivable set of laws, it loses predictive power. Some physicists argue that this leads to a form of anthropic reasoning, suggesting that our universe is one among many in a multiverse, selected simply because it permits the existence of observers like us. While this idea may be logically consistent, many consider it philosophically and scientifically unsatisfying. Another key criticism is that string theory is typically formulated in a background-dependent way. It assumes a fixed space-time geometry to define the behavior of strings. In contrast, general relativity is background-independent, meaning that space-time itself is dynamic and shaped by mass and energy. A truly fundamental theory of quantum gravity is expected to preserve this independence. While some progress has been made, for example in holographic approaches, many researchers view this as a conceptual shortcoming of current string formulations. A core requirement of a scientific theory is falsifiability, the ability to be proven wrong by experiment or observation. Critics argue that because string theory's predictions are so flexible and its scales so inaccessible, it skirts the boundaries of empirical science. As theoretical physicist Lee Smolin and philosopher Nancy Cartwright have pointed out, string theory may function more like a mathematical framework or research program than a testable physical theory. Furthermore, the adaptability of string theory to fit various observations after the fact, such as the cosmological constant or the existence of dark energy, can be viewed as a weakness rather than a strength. Without constraints that lead to specific, falsifiable predictions, some argue that string theory risks becoming metaphysics cloaked in mathematics. The theoretical landscape of quantum gravity includes rival theories that offer different answers to the same fundamental questions. Notable among them are loop quantum gravity, LQG, emphasizes background independence and quantizes spacetime itself. Causal dynamical triangulations, CDT, build spacetime from discrete building blocks in a non-perturbative way. And asymptotic safety suggests that gravity could be described as a well-behaved quantum field theory at high energies. While these approaches have their own limitations, their existence underscores the non-uniqueness of string theory as a candidate for a unified theory. In the face of these challenges, string theory continues to evolve and inspire new developments. Despite the criticisms outlined earlier, string theory remains one of the most active and dynamic areas in theoretical physics. Recent advances have extended its reach into new domains, offering both conceptual insights and potential bridges to observable physics. These developments suggest that string theory is not a static framework, but an evolving program that continues to shape our understanding of the universe. One major recent initiative is the Swampland program, which aims to distinguish physically viable string theory solutions, the landscape, from those that are inconsistent with quantum gravity, the swampland. Proposed by Kumran Vafa and collaborators, the program formulates conjectures, such as the weak gravity conjecture and the distance conjecture, to constrain low-energy effective field theories that can emerge from string theory. If successful, this approach could reduce the number of viable vacua and help restore some degree of predictability to string theory. The swampland ideas also have important implications for cosmology, such as placing constraints on models of inflation and dark energy. The ADS-CFT correspondence has evolved into a powerful toolkit for studying quantum gravity. New research has extended holographic duality to more realistic spacetimes, including attempts to generalize it beyond anti-de Sitter space. The ER equals EPR conjecture, which posits a deep connection between wormholes, Einstein-Rosen bridges, and quantum entanglement, Einstein-Podolsky-Rosen pairs, is another example of how string theory concepts are reshaping the foundations of spacetime and quantum mechanics. These ideas suggest that spacetime itself may emerge from more fundamental quantum entanglement patterns, a revolutionary notion that string theory is uniquely equipped to explore. Unexpectedly, string theory has found fruitful applications outside of high-energy physics. Holographic duality has been used to model strongly coupled systems in condensed matter physics, such as high-temperature superconductors and quantum critical systems. It also provides insights into the quark-gluon plasma and strongly coupled regimes of quantum chromodynamics, QCD. These interdisciplinary applications demonstrate that even if string theory is not the final theory of nature, it remains an extraordinarily useful mathematical framework. Efforts to embed inflationary cosmology within string theory have led to models like brane inflation, where the early universe's rapid expansion is driven by the motion of branes in higher dimensional space. Other research explores the role of moduli stabilization, the mechanisms that fix the values of the extra-dimensional shape and size parameters. Some of these models make tentative predictions that could, in principle, be tested through precision cosmological data, such as patterns in the cosmic microwave background or the distribution of large-scale structure. Efforts are also underway to develop a truly background-independent version of string theory. The string field theory approach and more abstract mathematical formulations, such as those using category theory or derived geometry, aim to provide a deeper, more foundational understanding of string dynamics without assuming a fixed spacetime. Though still in early stages, these attempts reflect a broader goal of aligning string theory with the principles of general relativity and quantum gravity. These recent developments suggest that string theory remains a vibrant research program, rich with conceptual innovation. String theory presents a fascinating paradox. On one hand, it provides the most comprehensive mathematical framework developed to date for unifying all recognized physical forces, including gravity. On the other hand, it has not, despite decades of research, produced a single unique, testable prediction. This duality raises profound questions not only about the nature of the universe, but also about the nature of science itself. A key criterion for a successful physical theory is explanatory power. String theory scores highly in this regard. It provides a unified picture where all particles and forces are different vibrational states of the same fundamental object. It also naturally includes gravity and resolves some singularities that plague classical general relativity. However, critics argue that the sheer flexibility of string theory undermines its explanatory value. If any number of physical constants and particle configurations can be derived from different compactifications, is the theory actually explaining the universe, or merely adapting to it? The boundary between theoretical physics and pure mathematics has always been blurry, but string theory has pushed it to the limit. Its reliance on complex and beautiful mathematical structures is both its strength and a source of concern. The fact that string theory has inspired major developments in geometry and topology suggests it is deeply connected to mathematical truths. Yet whether those truths describe the physical world remains uncertain. Philosophers of science have debated whether string theory qualifies as a scientific theory in the traditional Popperian sense. Its current lack of falsifiability and experimental predictions challenges the empirical basis of physics. Some suggest that the scientific method may need to adapt to accommodate frameworks like string theory, while others warn that such flexibility risks turning science into metaphysics. Despite its current untestability, some indirect avenues of verification remain possible. For instance, the discovery of supersymmetric particles at the LHC would support a core assumption of string theory. Future cosmological data might support string-inspired inflationary models, and advances in quantum gravity research, such as understanding the structure of spacetime or the resolution of black hole paradoxes, may provide circumstantial evidence for stringy mechanisms. In this light, string theory may be ahead of its time, proposing ideas that require future technologies to test. Rather than viewing string theory as a definitive theory of everything, it may be more accurate to describe it as an evolving research program, rich with ideas that could eventually lead to a deeper understanding of nature, even if it is not the final answer itself. It may also act as a scaffolding, a temporary, powerful structure that enables exploration of quantum gravity, holography, and spacetime emergence, which could eventually be replaced or refined by a more complete framework. Whether string theory is the key to unlocking the universe depends on how we define success. If success means a single, experimentally verified equation governing all physics, then string theory has not yet been delivered. But if success includes deep unification, mathematical consistency, conceptual innovation, and inspiration for future inquiry, then string theory stands as one of the most promising and ambitious theories ever developed. String theory is one of the most ambitious and comprehensive theoretical frameworks ever devised in the history of physics. It aims to unify all known particles and forces, including gravity, into a single mathematically consistent model. In doing so, it addresses some of the deepest questions in science, about the nature of spacetime, the origin of the universe, and the fundamental constituents of reality. The theory's strengths are impressive. It naturally includes gravity, resolves key singularities, incorporates supersymmetry, and provides insights into black hole thermodynamics and holography. It has also inspired profound advances in mathematics and led to new interdisciplinary connections across cosmology, particle physics, and condensed matter theory. However, string theory's weaknesses are equally significant. It has not yielded a single testable prediction that uniquely supports it over competing theories. Its dependence on compactified extra dimensions and the vast landscape of possible vacua leaves it vulnerable to the charge of being more flexible than predictive. Moreover, its reliance on unobservable constructs raises philosophical questions about its status as a physical, rather than purely mathematical theory. Ultimately, the question posed in the title, "Is string theory the key to unlocking the universe?" remains unanswered. The theory has opened many doors and illuminated previously hidden aspects of the cosmos, but it has not yet provided a definitive explanation or a clear empirical roadmap. It may be the key, or it may be part of a larger set of tools we need to fully understand the universe. What is clear is that string theory has redefined how physicists think about space, time, and reality itself. Whether or not it is the final theory, it has already changed the questions we ask, and in that sense, it has unlocked something profound.